Hi everyone. So today we'll talk about the energy cycle and seasons. Before I start today's lecture, I'm glad to see that like almost 90% of the class has participated in the first attendance quiz, and that means like almost everybody will be listed as present, and I hope that you'll continue to do so throughout the course. And again, if you're not able, if you are having any difficulties, like answering the quizzes or following the lectures, please like don't hesitate to reach out to me, and I usually respond to emails immediately. So today is we'll talk about the energy cycles and the seasons, and we'll actually dwell on very important concepts and weather and climate. So I'll start with the first, insolation. So there are a few terms I want you to learn, but I don't want you to memorize it. There's no need in memorizing these terms, but I just want you to understand the concepts behind them. So when we talk about insolation, for instance, many of you may have heard about this term used, especially and it's a very common term in climate science. So when we say insolation, we are actually only simply referring to the amount of solar radiation that's reaching the Earth's atmosphere, right? And so if we look at the Earth, for instance, where we have the interactions, the precipitation formation, the rain, and it feels like it's a closed system, right? But we receive the primary source of energy is from the sun, so that's from outside, right? And the solar energy is the primary source of energy, and then it really drives the sole driver of the climate system. So, and there are terms associated with the insolation, of course, and then there is absorption, for instance, where we have, which refers to the capacity of a body to absorb that energy, right? And then don't mind these numbers, but it's just to give you an idea of like, it's not like we receive, we're exposed to the 100% of the energy that's like that reaches the top of the atmosphere. It's because like only actually about 23% of it is incoming solar radiation is directly absorbed, right? By the atmosphere, it comes in contact, right? And many of it, as you see in the next slide, scattered, reflected, and because in the atmosphere we have different particles, right? And there are molecules that interact with this solar radiation. But remember, about 23% of the incoming solar radiation is absorbed. But when we're talking about, like, for instance, there are different interactions, right? For instance, there is about 48% of the incoming solar radiation passes through the atmosphere in a way because the atmosphere, it actually serves as the atmospheric window. In a way, it lets the radiation that's actually not harmful, right? And then it absorbs, and then the more harmful types of radiation, as you'll see in the next slide. And of course, not everything is absorbed, but of course, some of it is reflected, right? When we say reflection, it's simply the redirection of the energy that's coming from the sun, and about 35% of it is like directly reflected. Why is it reflected? Because it comes to in contact with different surfaces, not just the atmosphere, but also it reaches the surface of the Earth. There's always going to be reflection. But the mainly it's reflected by clouds, right? And aerosols, these are suspended solid particles in the atmosphere and in the Earth's surface. So clouds are also they have different molecules, particles within them, right? And scattering is also a form of reflection, but it's actually the only difference is that when we're talking about reflection, it's usually at an angle, right? But when we're talking about scattering, it's a reflection. It's more like a more random reflection of the solar radiation. So so it's just like when the solar radiation interacts with the particles that we have in the atmosphere, it doesn't necessarily just reflect, but in more cases, it's more likely for it to be scattered because it's because of the surface properties of those particles, right? And so why the sky appears blue is also has to do everything with scattering, right? So for instance, during the morning, when the sun is overhead, and it's just like the sky appears blue, right? But as the time progresses, and the sun is no more overhead, and most of the colors are already scattered, and then it appears as if the sky is more appear reddish, right? But scattering is also like remember, it's a form of reflection, but it's actually reflection is like only describes the passes at an angle, while scattering is results in a large number of weaker rays traveling in all directions. So, like I said, solar radiation is the primary source of what drives the climate, right? What drives the weather, right? And then to put it simply, where we have like the energy from the sun, and then we have different weather types because we also have gradients, right? And the gradient is very important, right? And different places receive, for instance, if you're in the high latitudes, of course it's colder in the high latitudes because the solar radiation is like more at an angle, right? But in the tropics, the solar radiation, the sun is more overhead, and it's always going to be warmer in the tropics compared to the high latitudes because the sun is overhead. But the solar radiation includes a portion of the electromagnetic spectrum, of course, and then it's actually divided into three ranges. We have, as you can see here, we have the more dangerous rays, for instance, the ultraviolet rays here, and then we have the visible portion and what we call the infrared radiation. So if we look at the atmosphere is actually without the atmosphere, life, the planet can't sustain life. Because if we're, for instance, to be exposed to UV radiation, it's actually going to be very difficult for life to exist, right? And then because these are very, very dangerous rays, but in a way, the atmosphere not only warms the planet, but also by serving as whatever species we have by protecting the life on Earth from this harmful radiation, it actually sustains life in this planet. And so if I ask you, for instance, what type of solar radiation passes through the atmosphere with little absorption by gases, it has to be the what type of solar radiation passes through the atmosphere with little absorption by gases in the atmosphere? It has to be the long wave radiation, as you see here in this figure. So in a way, the atmosphere is completely transparent for instance, this what we call the radio window, right? These are not harmful radiations, and it's just like, it's the atmosphere is completely transparent, while it's completely opaque for those like high resolution shortwave radiations, like the UV radiation, X-rays, and gamma rays, like, right? And then, for instance, we often talk about UV radiation, and in terms of the ozone layer, right? Because we have the ozone layer. We'll talk about it in the next lecture. But the fact that we have the ozone layer is one of the reasons that we are able to sustain life in this planet, because the ozone layer, by interacting with the UV radiation, it protects us from the UV radiation from reaching the surface of the Earth. And then, as you probably know, that if, for instance, we are exposed to the UV radiation, we can have all sorts of health problems, including skin cancer and then different problems associated with that, right? And then, but again, it's more like the atmosphere is a more like beautifully designed system, where it only, in its natural phase, it only allows actually those more healthy forms of radiation, like infrared, microwave, and radio waves, right? And there is also, of course, a very important concept that we need to take into account, but what we call albedo, right? So now we're talking about the proportion of the incident light of radiation that is reflected by a surface, right? We're measuring the capacity of a surface to reflect the incoming radiation, right? So if you look at different surfaces, for instance, whether it is like a desert or a savanna, or for instance, if it's a thick forest, or the ocean, the clouds, they have different capacity to reflect the incoming radiation, right? So, for instance, you look at here, the ice, snow, because this is a completely white surface, it is more has a very high capacity to reflect the incoming radiation, say compared to desert. We have, for instance, the surfaces that we see in Sahara or in deserts, right? Because the properties of the surface are completely different. So usually, white bodies are more likely to reflect the incoming solar radiation, right? So one of the problem when we're talking about climate change is that, as you also see in the Chasing Ice documentary, not only that, like, by when we global temperatures increase, the surface of the planet is also changing, right? So we're also changing the albedo and the albedo effect of the different surfaces, right? So, for instance, if you increase the temperature, of course, the ice, the snow is going to melt, and then we have a different surface which is more capable of, which can absorb the incoming solar radiation, right? So that means instead of that additional the solar radiation being completely reflected, it's like more and more heat is being absorbed, right? So that would cause more warming, right? And it's also extremely relevant in modern architecture, right? So if we look at, for instance, how our cities are built, right? And for instance, why it feels like extremely difficult to walk during summer in Atlanta, right? For instance, you won't be able to walk in the highway in Atlanta, right? Even if we don't really have any cars, because of the asphalt, right? So it's really, really relevant that we think about, like, for instance, the albedo effect of different materials, and then it would really help us, like, in combating like heat waves in cities, for instance, right? So if we have more green areas, for instance, right, in the city, it would be much more it would be much more helpful to tackle the extreme heat, right, compared to asphalt, for instance, where it's usually, instead of reflecting that extra heat, the extra radiation, it's like a very, very efficient at absorbing that extra heat. But if we have, like, for instance, concrete, then instead of asphalt, of course you would feel the difference, right? So I was asking my students, for example, in the previous class, where to compare cities in the summer, for instance, in Atlanta, and or cities in Europe, where it's much more common to have this concrete instead of asphalt. It's very, for instance, if you look at cities in Paris, you see these cobblestones, and so it's actually, when you walk, even if it is really hot outside, when you walk during summer, it doesn't really feel you don't really burn from the heat and from walking. And so this numbers, you see, are very important. For instance, when we really have to take this into account if we are to build new cities, for instance, because climate change is a major issue now. But when these cities were first built, like 200 years ago or something, and the issue wasn't as relevant as it is today. So if we look at the Earth's energy balance, right, in the grand scheme of things, so what you need to know is, you don't need to memorize this numbers, but I just want you to mention that, like, usually the Earth's energy balance, like, naturally, it knows how to attain a balance, right? So the problem with the climate change, the problem with the climate crisis is, like, we are actually emitting more carbon dioxide, more greenhouse gases, and then we are actually interfering with the Earth's energy budget, right? So instead of maintaining this balance, what we have is, because of, like, this additional greenhouse effect that is actually caused by humans, we are actually we're causing more warming, and then the Earth's energy system is out of balance, right? And so typically what comes in, and then it's actually matched by what's going out. So it's always the system is always trying to maintain that balance, but we are definitely off balance because we are emitting unnatural sources, right? And anthropogenic greenhouse gases into our system, and then we're pumping these greenhouse gases, and then of course it add to more, causes more warming that is unnatural. But the planet in its natural state knows how to maintain this balance at all times. So the very important concept in climate science is the feedback. So what I mean by feedback is, so we really have these interactions, right? So we can't really say we can't really view the climate system as if it is just a linear system, right? Where you have, for instance, you pump greenhouse gases, and then you only have like you can only expect a certain type of warming, right? But what we have instead is like we have this complicated, very complex feedback loops, right? So for instance, there is a positive feedback and there was a negative feedback. So I'll give you one example. So when we're talking about positive feedback, it's actually when you add something to the system really amplifies the original signal, right? So I'll give you an example. So think about driving downhill, right? You don't need to pump gas, right? Because the system is actually accelerating the original response, right? So it doesn't matter whether you're pumping gas or not, but the car would actually continue to accelerate, right? While negative feedback is the opposite, right? So if you're driving your car uphill, for instance, you need to maintain the constant. You need to give it more gas, right? That's because otherwise the system is actually pushing you against the initial condition, right? So instead of amplifying the initial conditions, it really dampens the initial response, and it kind of like tries to balance and to balance the initial condition. So you've seen this from Chasing Ice documentary. And so what we have typically when we're talking about positive or negative feedback is, so usually it's very, unfortunately, when we're talking about climate crisis, we have more of a positive feedback than the negative feedback. So what's happening in the high latitudes is, for example, we have a temperature rise, right? And then obviously that causes the sea ice to melt, right? So and then while doing so, and then you remember from the documentary where you have like surfaces, like the black surfaces are being exposed, right? And then that actually changed the albedo effect of the ice, of course, right? And then that means more heat and becomes absorbed by the surface. And instead of if it's completely covered by ice, for instance, it's like whatever is the incoming solar radiation is easily reflected. But now it is changing because the surface of the ice is changing, right? More melting exposes and a darker ocean surface, right? And then that absorbs more heat, and then that amplifies the temperature rise. So that means like a 2 degrees Celsius warming, for example, right? If we just like pump an initial condition where we have a 2 degrees Celsius warming in a short or long term might actually trigger a significant warming that's like double the initial amount, right? So that's a positive feedback. So this is actually like as if we're driving downhill, right? But the negative feedback loop, it's actually I'll show you more. I'll give you more example when we talk about more natural climate variability, and where we have over a very long period of time, the Earth tries to maintain a certain temperature throughout, right? And then but nowadays what we see with the climate crisis is it's just more of a positive feedback. Whatever we do, it's being accelerated, and then we have at the end of the day we have more warming, right? And these feedback loops are not fully understood because remember there's a lot of methane that's stored in the high latitudes, right, in the Arctic, right? So if the surface is completely changed, and if that methane is like exposed, if that methane now is like if when we have the ice, it's completely sealed off from interacting with the atmosphere, right? But if the surface changes, the methane starts interacting with the atmosphere, then there is a very a huge amount of methane will be released to the atmosphere, and then that would significantly increase global temperature. So it's one of our biggest worries in the climate in climate science, is that like this the extent and then of the positive feedback loops that we know. There are also other feedback loops we don't completely understand, right? Okay. But again, we will revisit these feedback loops again and again throughout the course. So now let's go to seasons. So I'm sure many of you know that what causes seasons, right? Well, what causes the seasons? Well, to put it simply, it's actually the tilt of the Earth, right? If the Earth is not tilted, right? If the Earth is not tilted, well, as you'll see in the next slide, it's just like that we wouldn't really have the seasons. So the what causes the seasons is because the Earth rotates on its axis and it's also tilted, and then we have a different portion of the Earth, and throughout the year is like exposed to different amount of solar radiation, and then of course that triggers changes like in vegetation, temperature, and precipitation patterns, and then that actually that controls the length, and then of course, and then how pronounced the seasons are depending on the where you're located. So a day in Earth on Earth is one rotation of the Earth on its own axis, right? So it takes about 23, not exactly 24 hours, but it's about 23 hours and 56 minutes. And then, well, it's just like a night on Earth is like as the Earth rotates on its own axis. Of course, a part of where we are, for instance, in Atlanta, some part of during the day, of course, one side of the Earth faces the sun, and then of course at night we're facing away from the sun, right? So that causes the days and night. But so why we have the seasons is like, of course, it takes about 365 days for the Earth like to travel or more revolve around the sun, and it's also because it is tilted, and it's always a portion of one portion of the Earth that's being exposed, right? Without the tilt, of course, like, we're just like, we wouldn't really have seasons. It would be just like half of the Earth would be completely dark and cold, and half of the Earth would be just like completely always at all times exposed to the sun, right? And remember, the seasons are not caused by how close the Earth is to the sun, because the relative changes in distance are actually like not relevant here. But as you can see in this GIF, what you see here is, you see, for instance, during the winter time, a portion of the Earth, like in the northern hemisphere, and facing away from the sun, while during the summer season, it appears that a large portion of the northern hemisphere, of course, we face the sun is more like overhead, right? So because of this tilt, and we have the seasons as the Earth revolves around the sun, right? And remember, there is also, we have this change in the tilt of the Earth. As we talk, we will have a lecture on natural climate variability that we will discuss this concept again. And then, of course, we have, on top of the seasons, these are short-term changes, right? But we also have changes that take place over thousands of years. right? And where we have actual differences and important differences in the distance between the sun and the earth. So this occurs over a very, very long period of time, and then there are variables very closely related to the earth's tilt, change in the earth's tilt, that cause what we call the ice ages. But we have a lecture or two entirely dedicated to that. But the seasons, for instance, in Atlanta, for example, okay, we can say we have 4 seasons, right? We have the summer, spring, the autumn, and the winter season, right? And but in many places, in many other places, like in the northern hemisphere, these seasons are actually not necessarily expressed in terms of temperature. They're actually more the most relevant variable is actually, instead of temperature, it is precipitation, right? So there are places like in Asia, for instance, it's very common. The seasons are typically divided in. The Asian continent and in Africa typically have 2 seasons, right? You have the rainy season and then the dry season, and then temperature changes, are not as significant. But here, and then while you move closer to the northern high latitude, to the tips of the northern high latitude, you have those significant changes in temperature, and then temperature is more relevant here. Even in Atlanta, right? We see significant changes in temperature between like spring, winter, and not so much between autumn and summer here in Atlanta. And then it's also one of the consequences of the climate crisis that, we see in many places significant change in the duration of the winter season and the spring season, right? It's like because of the additional warming, it's more the summer season and the autumn season are more longer, and then while we have shrinking winter in many places. But how it is expressed in other parts of the globe. So, for instance, if we look at summer season, and if we look at global wind patterns, and during the summer, typically what we have is the land surfaces here. This is continental Asia. Here is Africa, and then here is the North America and the South America here, right? And then we have Australia here. Remember, during the boreal summer, right? That's like when the sun is overhead, closer to the moving, like the close in places like, for instance, in countries like Ethiopia, or we have in East Africa, many places actually the sun is overhead. In the northern hemisphere, actually the sun. We have low pressure systems, so low pressure systems developing in these parts of the northern hemisphere. So what happens is, because again, it's like I told you, I gave you an example where when you open a fridge, you see that the wind, a cold air coming out, right? So it's exactly like that. We have high pressure cells, winds from the high pressure cell points to the low pressure points, cell points, and then at the end, what we have is this movement of winds. Of course, since the winds are coming from the ocean, what we have is enormous amount of precipitation in what we call this the monsoon regions in Asia, East Africa, and West Africa, right? And then what happens during the boreal summer is that we have the complete reversal of these winds, right? Now it is cold in the northern hemisphere, right? Many places in the northern hemisphere, while it is warmer in the southern hemisphere, right? So this time of the year in southern hemisphere, if you think about if you go to, for instance, cities in Brazil, it's really warm, right? The sun is overhead in the southern hemisphere when it is colder during the winter season. So what we have is a complete reversal of these patterns, and then we have more precipitation, the monsoon moving southward, right? So in these places, in many places, it's more precipitation is more relevant, right? And then the gradient in temperature, and then the fact that, like, the some places are warmer because of the seasons, it really creates, governs the movement of winds, right? And because of it, we have the monsoons in Southern America, and then in the Southern Hemisphere, Northern Hemisphere, at different times, right? That's it from my side for today. And next lecture, we'll talk about the composition and structure of the atmosphere. And again, like I said, we'll revisit the feedback loops again and again throughout this course. Once the lecture video is posted on Wednesday, of course, I'll post the attendance quiz for the week, and you know where to access it. And I would also, I hope that you have also completed the attendance quiz that was posted as part of our efforts to improve the introductory courses offered by our department, which is not necessarily part of this course, but to get 1 extra point. I hope that you have completed that quiz as well. If not, you'll also get an opportunity to do a quiz to get an extra point, right? I'll see you on Wednesday.